at the position of the negative charge. And then there's going to be like that, right? If I were to just think about this classically. So there is a force on this charge due to the electric field that's created by this charge, and a force, and a magnetic force generally due to this. But this force, the magnetic force, depends on the speed relative to the speed of light, if these guys are of the same order, okay? And so this is kind of a relativistic effect. In other words, unless the electric field is zero, or much, 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 much smaller than the magnetic field, electric forces completely dominate over magnetic forces until the particles are moving close to the speed of light. So this is a small correction. And we'll come back to it. Our next topic is perturbation theory and thinking about the corrections to small perturbations to a Hamiltonian due to small forces. But the dominant force is electric. Okay? And so that means that the dominant force here is due to the electric field, which we express in the potential in terms of electrostatic potential. And that electrostatic potential is the product of the charges divided by the distance between the charges. Okay? There's a 1/4 pi epsilon naught if you're so inclined. Okay? So that's our Hamiltonian approximately ignoring any magnetic effects, the relativistic corrections to the problem. Okay. Is this Hamiltonian separable in the 2 degrees of freedom, one for the positive charge and the negative charge? No, it's not, right? Because we have this term here. It's not the sum. This is not equal to a Hamiltonian for the positive charge entered the identity for the other. Okay? It's not of that form. It's not separable. However, as you know, for the 2-body problem, it can be separated. And in terms of different degrees of freedom, in terms of the center of mass and relative coordinate. Okay? So we change variables. We have a relative coordinate and a center of mass coordinate. I'll call that little x and big X. Okay? That's the center of mass. So we have, let's come over here. So the center of mass position and the relative position, little x, and I'll call that the way I'm drawing it, going from the positive to the negative. Okay? So, re-expressed in those coordinates, what is the Hamiltonian? Okay? So, to do that, let's write down what are the conjugate momenta conjugate to these coordinates. To find that, the easiest way to do it is to write down the Lagrangian. So Lagrangian is 1/2 the kinetic energy of this, the kinetic energy of the negative charge, minus or potential, minus potential is that, Okay? And when I re-express that in terms of the, re-express that, solve for x plus and x minus in terms of the center of mass and relative coordinates, you get the following. I'm not going to go through the algebra, it's pretty straightforward. Where capital M here is the total mass, and mu is the reduced mass. Okay. Of course, remember, the reduced mass is kind of like adding the masses in parallel, if you think about them like resistors. So this is dominated by the smaller mass, okay? So if the mass of the negative charge is tiny compared to the mass of the positive charge, then the reduced mass is essentially the M minus, right? And the center of mass is almost all at the position of the heavy mass. Okay? We'll come back to that in a moment. Okay, so with that said, what we see here is that the momentum conjugate to the center of mass is the total mass times the velocity of the center of mass, and the relative coordinate momentum conjugate to the relative coordinate is the reduced mass times the velocity of the center of mass, right? So that means once we do that, we can re-express the Hamiltonian once we make that substitution. So we have this is my Lagrangian, and then I transform to the Hamiltonian, and I get the following. I get the center of mass momentum squared divided by twice the total mass plus the relative momentum over twice the reduced mass plus, or sorry, minus q plus times q minus over the magnitude of the relative coordinate. Okay? And this is separable. Okay? So this Hamiltonian, the two-body problem, is separable. We knew that from classical dynamics, but we just redid it. So this is the identity on the center of mass transferred into okay? So this is separable. Which means that there are eigenstates of the Hamiltonian, which are product states, separable states, for the center of mass degree of freedom and the relative coordinate degree of freedom. Okay? So this is H center of mass, and this is H relative. And so if I look for eigenstates of the Hamiltonian, I can separate them into product states of center of mass and relative coordinate. So when looking at stationary states, And that energy is the sum of the energy of the center of mass and energy of the relative coordinate. Okay? So the energy of the center of mass, what are its eigenstates?
Just the free particles.
Free particles, right? So these are free particle eigenstates. And these energies are just p squared over 2m, the center of mass momentum. So we can write, for example, momentum eigenstates as possible energy eigenstates of center of mass. Typically, one ignores this. Typically, one treats the motion of the center of mass classically. Now you can think about why that's true. Why is that a reasonable thing to do? Well, typically we're talking about room temperature, atoms running around. Their de Broglie wavelength, if they're in a thermal state, their de Broglie wavelength or the coherence length is very small. So there's very little quantum interference that would be possible in terms of the motion of a thermal atom, okay? But in recent years, recent decades, we've understood how to cool atoms, not just a solid, like a dilution refrigerator, but individual atoms, and cool them so that their coherence length starts to become important, and we can have interference between the whole center of mass of the atom. That's the whole business, for example, of laser cooling and Bose-Einstein condensation and all of these things. So in laser cooling, the whole story is about the quantum nature of the center of mass of the whole atom, okay? But that's not going to be our focus here. Right now, we want to talk about this part, the quantization of the states of relative motion of the negative charge relative to the positive charge. That is to say, in hydrogen, the motion of the electron relative to the proton. Yeah?
Should those be over del x dot?
They should, yes, thank you. Yeah, they should, absolutely. Thanks for noticing that. All right, so with that said, we're going to focus on this interaction. We're not going to look at the center of mass for a moment, and just forget about the rel label here, and just understand that these coordinates are the relative coordinates. Okay, so the relative coordinate, sure, time independent from the equation. Alrighty, so we got this, which has this form, where R is the magnitude of X. Okay? And so this potential is a central potential. That is to say, the potential energy only depends on the length of the position vector, the distance between the two particles, and not the angular coordinate. Okay? And we studied that, sort of, last semester, to remind ourselves about those things again. what is natural when we have central potential is to express this kinetic energy in terms of radial and angular kinetic energy, which is what we did. So let's rewrite that. There's a radial momentum component, and then there's an angular momentum component. And then the potential. Moreover, when we have a central potential, because of this, we know that the Hamiltonian, in this case, commutes with L squared, and the Hamiltonian commutes thus with any one component of orbital angular momentum, right, LZ. Which means that stationary states of the Hamiltonian are also stationary states of L squared and LZ. That is to say, we can separate the solution here as a radial wave function, which actually depends on L and Lm. Okay? So with that kind of separation and expressing that, now remember the radial wave function we have written in the past in terms of the so-called reduced radial wave function. Okay. When we do that, we can re-express the Hamiltonian, as we did, as a kind of Schrödinger equation, the representation here, with an effective potential that depends on L. Where the effective potential is the true potential plus the angular momentum barrier. Okay? And this is a Schrödinger equation on the half line where R is positive. Or non-negative. Okay? So in our separation here, we have that the wave function is the radial wave function, which I've written this way, times a YLM. Okay? So this is the form of the wave functions of the stationary states, or it is a form, right? We can write, of course, we can look at different kinds of separations, but this is one. All right, let's take a look at this explicitly. Let's look at this, guys. So our Schrödinger equation, what do we have for our V effective? So we have a 1 over R potential, right? So we have something that's falling off like 1 over R. And then we have, for a non-zero value of L, we have some kind of angular momentum barrier. And the total effective potential is the sum of these. So this is the total potential I've drawn. And what we see here is that there are going to be bound states for E less than 0, the way we define our potential to be 0 at infinity, with a 0 potential at anything we like. We choose it to be at 0 at infinity. And then above here, unbound states. And they are in the continuum. There is no quantization of energy. There's all possible energies are possible for the unbound states. Okay? So let's talk, we're going to talk about, for the foreseeable future until late in the semester, the case of the bound states. Okay? So for the bound states, E is less than 0, we'll call that minus E sub B. Okay, so this is the binding energy. So E sub B is a positive number. All right. Okay, so our Schrödinger equation and I'm going to put, for the case of the bound states, there is another quantum number at least that defines which one for a given L, right? There's a discrete. So there's a radial quantum number, which are called M sub R. Okay. Of course, we know that there is necessarily a degeneracy of at least 2L plus 1. Why? Well, we have this rotational symmetry, right? And since we have this rotational symmetry, it doesn't matter what axis we choose. This thing, if I rotate around as the axis, I get the same thing. This Hamiltonian depends nowhere on M, the N quantum number. See that over here, it only depends on L. So there are two L plus 1 different states that must have the same energy. So the degeneracy is at least, for any central potential, every state has a degeneracy that's at least 2L plus 1. Okay, so now we want to get going and solve this. The first thing that we should do is make the problem dimensionless. As I've emphasized, we did this in the context of the harmonic oscillator. The first thing you should always do is identify the physical scales in the problem that are defined by the constants, the fundamental constants of the problem, and then get rid of them. And then define everything relative to those scales, okay? Now we can do this in general for an arbitrary two hydrogenic atoms, whether it's positronium, uranium, or hydrogen, but I'm going to focus here on hydrogen. And in your homework, you'll look at more general situations. So let's look at hydrogen. So in hydrogen, Q plus equals Q minus is E. Okay? And the mass of the electron, what is it, a half an MeV in C squared? And the mass of the proton is a GeV, I think. Don't remember.
Roughly, yes.
What?
Roughly.
More or less. So this is tiny compared to this, right? So in this problem, the reduced mass is almost equal to the mass of the electron. There's a tiny, tiny correction due to the fact that the mass of the electron is finite compared to the proton. But pretty much all the mass of the hydrogen atom is in the proton, right? The center of the mass is almost essentially the mass of the proton in this case. So with that said, in this case, we can think about, it's approximately true, that the center of mass is almost exactly at the proton. And the relative coordinate goes from the proton to the electron. And that, so we can think about it approximately this. Here's the center of mass, approximately. Here's the electron, here's the proton. Okay. So in this case, we can think about, and we often do, when we're talking about the degrees of freedom of the hydrogen atom, we call them the electronic degrees of freedom, because we're thinking about it as the electron moving relative to a fixed proton. Although that's not exactly correct, it's really the relative motion of both relative to the center of mass. The center of mass is almost completely at the proton. Okay? So with taking that correction, you know, to good approximation, this is for the hydrogen atom, we write this as this equation where this is the mass of the electron. Okay? So we don't put the m sub e in there. That's just understood that this is the mass of the electron. And this I think about as the electronic coordinate relative to the proton. Okay? All right, so now we want to get rid of the units.
Should there be two?
There is, yeah, there's a 2m, sorry. Thank you, this is just totally screwed up. All right, so with that said, now let's make this dimension. How are we going to do it? So what we have are, this equation is defined by constants, fundamental constants. We have the charge of the electron, or minus the charge of the proton. We have the mass of the electron, and we got h bar. Okay, those are our constants. If we wanted to work in SI units, we'd also have epsilon naught, then I'm not. Okay, and we then think, well, how do we make a characteristic length and a characteristic energy out of these constants. Okay? That's a skill. It's a skill to develop. It's a useful skill. It gives you a sense of the whole problem. What are the scales? How big do we expect a hydrogen atom to be? We can get that just from this numerology without solving anything. Okay? So we could do that in the following way. One way to do it is as follows. Let's just define, let A naught equal the characteristic length scale. And let's let E naught be the characteristic energy scale. And I will define the dimensionless R as whatever the R is in units of A naught, and the dimensionless energy, binding energy, as the binding energy over E naught. Okay? So these are dimensionless. So now we can just plug that into these definitions into our equation. And we get the following. Minus, so I'm going to factor out here. We got h bar squared. I'm sorry, that's not what we got. There is an h bar squared here. I screwed that up, didn't I? They should all have an h bar squared. Right? Because it's h bar times the derivative of this little thing. Sorry. Now it makes sense. Always thinking ahead. But so now I'm back at h bar squared over the mass of the electron times A naught squared times minus a half d by r squared. I got minus e squared over A naught times 1 over dimensionless r. And then I have plus h bar squared over n k squared times L plus 1 over 2 dimensionless r squared is equal to minus E naught times the dimensionless binding energy, I'm sorry, times the wave function. Right? So that's just factoring out the characteristic scales. And I can make everything easily dimensionless by choosing having E naught be both equal to this and E naught equal to this. It's two equations, two unknowns. I have to solve for A naught and E naught. And by choosing those equal, dividing everything by E naught and making all these coefficients 1, then I got rid of all the units. And when you solve that, what you find is the following. A naught is h bar squared over me squared. And E naught, I'll plug that in, that's n e to the 4th over h bar squared. Those are the characteristic length and energy that come from these three fundamental constants in CTS units. Okay? And what are this? This is equal to a half an angstrom, approximately. It's the Bohr radius. This energy is 27.2 electron volts. We also define this as equal to, if we define E naught over 2 is defined as the Rydberg. Which is 13.6 eV. That's just the definition that comes out. We'll see in a moment. So just from numerology, just from the constants in the problem, we essentially get what the size of the atom is and the binding energy. It's the whole story. So now we solve the Schrodinger equation. Okay? So, I encourage you to think about those kind of skills because it's just such important when you're doing any physics problem to first think about what the scales are in the problem. Yeah?
I know that there is a Rydberg energy, but what step, what concept will allow you to go from E naught to E naught over 2?
Nothing. Nothing. No, that's just a definition. There's no there's nothing there. I'm saying that will come out of the Schrodinger equation. Effective when we solve it, which we're about to do, we'll see that that is a constant that appears. But there's nothing in this dimensionless analysis that tells us, oh, it put out E naught over 2. That's a good thing. There's no way to go. There's no logic there. I mean, it's still the case, even without E naught over 2, this is the right scale. A factor of 2 is, we're friends, it doesn't matter. You might think I'm not a friend, but anyway. All right, so now we are at the point where we can try to solve this, and we'll just get started on it and we'll finish it next time. So let's take a look at our equation. So in dimensionless form, we have the following equation. Minus a half d by the dimensionless r squared plus L times L plus 1 over 2 dimensionless r squared minus 1 over r times the reduced radial wave function is equal to minus the binding energy, dimensionless binding energy. Oh, by the way, this thing has a name too. It's called the Hartree. So the Rydberg is half of the Hartree. So these are known as atomic units. You may have heard of Hartree-Fock. It's the same guy. He was first in atomic physics looking at many-body electron effects, which now became standard in many-body physics. But this is a Hartree. It's 27.2 eV. All right, so this is the problem we want to solve. And I'll remind you of something we talked about last semester about the asymptotic properties of the reduced radial wave function. Okay? So to get at this, to solve for this equation, we'll solve it as a function of the dimensionless variables. We first analyze the asymptotic properties, okay? And we can get them simply from the Schrodinger equation. So when asymptotically, as we get close to the origin, this, if L is not equal to 0, this dominates. The angular momentum barrier dominates over the 1 R. Okay? So this means that we have this approximate equation. And so, asymptotically, it must be the case that this thing, for a given value of L, as we showed, the term that doesn't blow up has to go like R to the L plus 1. That is a solution to this equation that doesn't blow up. So, we have that behavior. What about as R goes to infinity? As R goes to infinity, well, the potential is tiny. So we can just ignore it. Well, that's an equation we can actually solve. Okay. This equation is equal to minus 2 finding u to 0. Okay. What's the solution to that equation? Exponentials, right? So the solution to this equation is that this is some constant e to the minus kappa r plus e to the plus kappa r, where kappa is the square root of twice the binding energy. Okay? Now, asymptotically, if we're talking about a normalizable state, we can't have this. It can't blow up. This we reject because it can't blow up. We can't have a normalizable state. So, what we've learned from this, and I'll conclude there, and we'll pick this up afterwards, is the following. The reduced radial wave function as a function of the radial coordinate goes like r to the L plus 1, e to the minus kappa r times some function of r, where this function is a constant as r goes to 0 and does not blow up faster than e to the plus kappa r as r goes to infinity. Okay, then it has the right asymptotic properties. And it is this that is going to define the quantization, because in order to satisfy this boundary condition, there will only be a discrete set of functions that are consistent with that boundary. We know that the boundary conditions define the quantization. And so the rest of the story in solving this is to find those functions. And